Okay, dear colleagues, let's start our BIMS integrable system seminar, and today is the last seminar of our spring term. So today's speaker is Fehér from Hungary, and today he will tell us about Bi-Hamiltonian structures of integrable many-body systems via Poisson reduction. Laszlo, please, you are welcome.
Thank you very much, Dima. So I am happy to be here. So my second time in China, and I enjoy it, and this very nice surrounding, fantastic infrastructure. Okay, so let me. Sorry, some technical problem. So I'm going to talk about this Calogero-Moser Sutherland type and Toda models, which are many particle models, particles moving on line or circle, and they are integrable for any number of particles, and some of them are extended by internal degrees of freedom, so-called spin degrees of freedom. And these are somehow related to many interesting areas of mathematics and physics. As one of the central figures in the subject, Simon Ruiz analysis, often say that they lie at a crossroad of mathematics and physics. And one of the simplest examples is this. I'm talking at the level of classical Hamiltonian mechanics. So one of the simplest examples is so-called Sutherland model or Calogero-Sutherland model, and particles moving on the circle with this potential exists some coupling constant. And it is well known that this model can be obtained by projection method or Hamilton reduction method from free particles moving on the unitary group UN in some canonical Riemannian metric. And I'm in a lucky position because last week Dima was talking about sort of close related subject, actually, in which he described the background of Hamilton reduction that I'm also applying in this talk. Okay, so this model arises by looking at free particles on the unitary UN and fixing some conserved quantities which are given by some moment map to some very particular value. And if you fix the moment map for the conjugation action of the unitary groups to arbitrary value, or if you don't fix at all, just take the quotient of the phase space by the symmetry group, which is a unitary group acting on the conjugation by conjugation, and that lifts it to the phase space, the cotangent bundle, then you get the so-called spin Sutherland model. When this phi is in my convention here is Hermitian matrix, which is also dynamical variable. So the point what I want to say that it is well known how to obtain these models by method of Hamilton reduction. And a few years ago, I realized that it is possible to have a modification of this reduction treatment, which is such that the same models will result, but they will be equipped with two different Hamiltonian structures, two different Poisson structures, which appear which form a Bi-Hamiltonian structure. So this is the topic of my talk. So just very quickly, so some other example, the open Toda lattice of Toda molecule, which was one of the examples of last week, or rational Calogero model, axis coupling constant, or trigonometric Ruiz-Schneider system, which at the quantum mechanical level related to the Macdonald's polynomials, or its hyperbolic version, which at particular values of the coupling is related to sine-Gordon solitons. So this somehow shows that these are important models related to interesting topics. So I mentioned that I will talk about Bi-Hamiltonian aspects of these kinds of models. So let me just recall, because maybe not everybody is working on this, what we mean by the Bi-Hamiltonian system. So we have some classical phase space, and the functions, say real smooth functions, are equipped with two Poisson structures, two Poisson brackets, such a way that the time evolution of any observable can be written in Hamiltonian form with the two different Poisson structures and two different Hamiltonians. And in addition, we require that these two Poisson brackets are such that an arbitrary linear combination is also a Poisson bracket. So the Jacobi identity is also satisfied for arbitrary linear combination. Then we say that this is a Bi-Hamiltonian system. And it is known that many classical integrable Hamiltonian systems are actually Bi-Hamiltonian. And this is one of the one of the several unifying principles of integrable systems, the Bi-Hamiltonian idea. And one basic fact here is the so-called Magri-Leonard scheme or recursion relation, that suppose you have some series of Hamiltonians, H1, H2, H3, etc., and they satisfy this relation. So with arbitrary, the dot means that you can put an arbitrary function, and so the Hamilton vector field of Hm with respect to second bracket is the same as the Hamilton vector Hm minus 1 with respect to first bracket. And if this is so, then it's very easy to see that it follows that these Hamiltonians Poisson commute with respect to both brackets. So they have a chance to generate the commuting Hamiltonians of an integrable Hamiltonian system. And this simple mechanism works in several examples. The first example, when this was actually discovered, was infinite dimensional Hamiltonian system. It was discovered by Magri. I am not totally sure now in what year, something 71 maybe, or something like that, long time ago, when he was studying the Korteweg-de Vries equation, this famous soliton equation, shallow water waves in a narrow channel. And one of the Poisson structures is the so-called Faddeev-Zakharov Poisson structure like this, and the other one is this one, which is actually correspond to the dual of the Virasoro algebra at some particular value of the central, of the Casimir, basically the central charge. And this system is Bi-Hamiltonian. The time derivative, the evolutionary derivative can be written with these two Poisson structures and two different Hamiltonians. And actually one has infinite series of Hamiltonians to satisfy this recursion relation or linear Magri scheme. All of them are integrals of some local densities formed from the KdV field. So this was actually the first example. And in several other integrable hierarchies, this kind of structure is present. The Dirichlet-Sokolov hierarchies and generalizations constructed more recently by Victor Katz and collaborators. They often have this Bi-Hamiltonian structure. Now, I will be using a very well-known little lemma for constructing such Bi-Hamiltonian structures, which I'll tell you this lemma here. So suppose we have a Poisson algebra, Poisson bracket algebra. So functions also are faced with Poisson bracket. And we also have a derivation basically given by a vector field of the phase space, derivation of the functions which form this Poisson algebra. So we have this Poisson bracket, then we can take the Lie derivative of the Poisson bracket. This is actually the Lie derivative of the Poisson tensor, but it's written like explicitly written, this new bracket. You take the derivative of Poisson two functions, derivative of, so I mean, this is actually a formula. This is actually Lie derivative in geometric language. And this derivative bracket is automatically, of course, anti-symmetric, satisfies the Leibniz identity, but in general, it is not a Poisson bracket. But if it is a Poisson bracket, that is, if it satisfies the Jacobi identity, then it's automatically compatible with the original one. So if this Lie derivative gives a Poisson bracket, then an arbitrary linear combination of the original one and the Lie derivative also satisfies the Jacobi identity. And several examples of compatible Poisson brackets can be constructed in this way. For example, in the KdV example, the first bracket is the Lie derivative of the second one. Then the derivative of the basic variable, the KdV field, is just this. So I will be using this mechanism to construct compatible Poisson structures in the context of many-body models. Now the rest of my talk, the pen of my talk is here. So I will spend some time on the first example when I notice what I'm talking about, which has to do with the spin-Sutherland model, which I have shown on the first slide, which comes from reduction of cotangent bundle of UN. But I will put a Bi-Hamiltonian structure to cotangent bundle of UN and reduce that. And then, depending on how quickly I proceed, I will talk about two other examples, similar construction. In another example, I take GLNC group, but regard as the realification, if you like, of this complex Lie group, cotangent bundle of that. And from this, I will construct some novel kind of spin-Sutherland models. Well, they are also known, those models with two-spin or two-sided spin-Sutherland models, as people call it, but here they will come together with Bi-Hamiltonian structure. And then, if I even have more time, I will consider the cotangent bundle of GL and R and get some Bi-Hamiltonian structure on this associative algebra, which has to do with the open Toda lattice and also with the so-called full symmetric Toda lattice. Okay. And probably I won't have to explain some technical details. I have some appendix about technical details. Okay, so now coming to the main point. So we take this cotangent bundle, and we trivialize the cotangent bundle by right translations, and also I mean identify the dual of the Lie algebra of the group UN with the space of Hermitian matrices, and the pairing. So the pairing is through this bilinear form. GLNC is regarded as real Lie algebra. So let's put this bilinear form, the imaginary part of the trace, And in particular, this allows you to identify the dual of the UN Lie algebra with the dual of the anti-Hermitian matrix with Hermitian matrix. So the trace will give you a real number there. Okay, so this is some basic object, imaginary part of trace. And so this is just some preparation. I have to do some preparation. So this GLNC real Lie algebra is vector space direct sum of two subalgebras. One is the unitary Lie algebra, other is this special kind of Borel subalgebra, which means here just complex upper triangular matrices with real entries along the diagonal. And this is actually a so-called Manin triple. This non-degenerate invariant bilinear form vanishes on these two factors, and they are actually dual spaces to each other with respect to that bilinear form. Okay, so if we have any element of GLNC, we can uniquely decompose according to these two subalgebras. And now, since our phase space is this M, this fracture, or how do you call it, the cotangent bundle of UN group, and I will write two Poisson brackets on this phase space. So in this Poisson bracket, derivative of functions appear. So we have derivative with respect to the first variable and derivative with respect to the second variable. This is notation. So the first variable is group valued. So this formula here defines left derivative and right derivative with respect to the first variable, and these derivatives are Bn valued or Borel value, the dual of the UN Lie algebra. And here it is just linear derivative with respect to this L is Hermitian matrix. So here the derivative is just unitary Lie algebra value. Okay, by this pairing. So maybe you don't need to remember the detail. The point is that this D1, D2 means derivative is the first and second variable. Okay, and then the first statement is that we have two Poisson brackets on its space of functions. the first Poisson bracket is actually just the canonical Poisson bracket of the cotangent bundle written in this invariant notation. You can see here the Lie Poisson bracket of the U and EH, which is part of the game, yes? Previous, yeah. My hearing is not very good. So this is one parameter group, and you take derivative. And with the secondary, just linear derivative along this curve. Okay. Can I go? So it is standard left and right derivative on a group, actually. But maybe you denote it by nabla. I mean, what else? The derivative is linear in the tangent vector of this curve is x, and linear in that. Okay. But there will be lots of, so I mean, so you can just see that this is the Poisson bracket, and this means that this really means that this second variable is a real set of variable, so it generates left translations on the group value variable, because this is the moment left for the left multiplication action. So this is the canonical Poisson bracket, and then I claim that there is also the second Poisson bracket, and you can see that the second Poisson bracket, so this is just matrix multiplication. So the second, and this is just decomposition with respect to this money in triple, the UN part. So you can, if you evaluate the second Poisson bracket for matrix element functions of G and L, then you will see that this is called quadratic in this basic variable. You can also see it here. It's called quadratic. The first one is a kind of linear Poisson bracket. The second is quadratic. Now, I don't think I want to spend time on how this Poisson bracket comes from. Although I have written the total details, but it takes time. So the second Poisson bracket also has a group theoretic origin, that you take the so-called Heisenberg double of the standard Poisson group N, which is actually GLNC as a manifold, and then you get the second Poisson from there in some neighborhood of the identity and analytic continuation. So I don't have time to explain it in detail, but the point is that the second Poisson bracket also it has origin in the theory of Poisson Lie groups and some analytic continuation. It is explained here, but I don't want to go into that because I have a lot of stuff. If you like, you can have a look. You can ask me. Now so we have two Poisson brackets on our phase space, and now let's define this derivation. So in order to define derivation, it's enough to define the derivative of the basic function. This is the matrix elements of our two matrices which form the phase space. So let's define it like that. In other words, this derivation is just the derivation along the vector fields for which this is the integral curve. And then it is a simple calculation to show that the first Poisson bracket, the canonical cotangent bundle Poisson bracket, is the Lie derivative of the second one along this derivation. So this guarantees that the two Poisson brackets are compatible by this basic lemma which I mentioned. So we have these compatible Poisson structures, the cotangent bundle of UN. And to my surprise, this paper was published in Letters in Mathematical Physics, and I thought that this must be known, but nobody told me that this is known. It is some kind of simple observation. And now let's consider Hamiltonians. Remember that L is Hermitian matrix, so we can just take this trace of various powers of this Hermitian matrix, and these Hamiltonians turns out that they satisfy this recursion relation with respect to the two Poisson structures. So it means that these Hamiltonians Poisson commute with respect to both Poisson structures, and the flow generated by the Hamiltonian vector field, which is defined through this relation, is just this orbit of one parameter group, the group UN. It's some usual flow, usual in integrable systems. Okay, so now I have this Bi-Hamiltonian system on the cotangent bundle of UN, and now I'm going to apply reduction to this system. Reduction in the same way as Dima was explaining a week ago. So basically, the reduction means that we have to specify a symmetry group. In this case, the symmetry group is UN, and we let the group UN act on our phase space in this manner. And eta is an element of the group UN, and it's just like by conjugating both of those matrices. And it turns out that then the reduction means that we just take to keep the observables which are invariant under this symmetry, the invariant functions, or geometrically speaking, we take quotient of the phase space by this action. Of course, the quotient space is not a smooth manifold, but we can talk about that. And it's a not totally obvious fact that the invariant functions form a closed Poisson subalgebra with respect to our compatible Poisson structure. So for the first Poisson structure is obvious. For the second one is not so obvious, but one can show it either directly or there is also a group theoretic explanation of that also. So we have compatible Poisson brackets on the space of invariant functions. Okay. Now, as I already mentioned, take the quotient of the phase space by UN. And now, in order to describe this, have some kind of effective description of this quotient space, well, we do something which is just to make life simpler or manageable. We restrict to the regular part of the group UN. So we restrict to unitary matrices which have n distinct eigenvalues. This is this UN reg. So this is a dense open subset of our phase space, and we just take the quotient of these regular. Of course, every function can be recovered by its restriction there. So in a certain sense, we don't really lose information, but it is just a simplification. And so if we are in this regular part, then we can choose representatives of the UN orbit in such a way that we diagonalize the group element. And this will be, this Tn is the regular part of standard maximal torus of UN. So diagonal unitary matrices with distinct eigenvalues. So every invariant function on the regular part of the phase space can give rise to a function on this gay slice, kind of physically, we use this terminology in physics or mathematical physics or even in mathematics. And actually, the restricted function will be still invariant under those symmetry transformations which preserve this phi. Those symmetry transformations are given by the normalizer of the maximal torus inside UN. So in this way, you show that the UN invariant functions on this regular part of the phase space is the same as the n is a normalizer of the maximal torus inside UN, as the functions on the smaller phase space, this K slice S, which are invariant under the normalizer. So we are going to represent the invariant functions by functions defined on this K slice S, which are subject to this residual symmetry. And now we obtain two abelian, two compatible Poisson brackets on these invariant functions on our gauge size by this usual procedure. So if we have I mean, every function is of gauge size with restriction of an invariant function on the regular part. This I is embedding of our slice into the phase space. So this F circle iota, not iota. This is restricted function. So the reduced Poisson bracket of the restricted function is by definition the original Poisson bracket. We take the original Poisson bracket restricted. And this gives Poisson structures on the space of functions. And the first is the thing is one thing is to have an explicit formula for that, for the reduced Poisson structure. And the explicit formula is that will be the next result. It's kind of interesting because it contains an interesting object which is a well-known dynamical classical R matrix. So this Q is just an element of the regular part of the torus of UN, this capital Q. And this RQ is a linear operator in GLNC, which acts like this on this matrix. JK is written like this in terms of the cotangent hyperbolic function, X-based function. Then this Q is exponential based. And then introduce this definition, which is people who are familiar with it, constant R matrix. R matrix bracket, which is used in the theory of Semyonov-Tianshansky, for example. But anyway, this is just the definition. So now I want to write a formula for two functions which are defined on this gauge size S. And here is the two reduced Poisson bracket. The formula is here. Just I have to. So the point is that these are relatively simple formulas contain the dynamical R matrix. And again, the D1 and D2 derivative is the first and second variable. The derivative with the second variable is as before. You shift the second variable by some arbitrary. You take derivative along this line, and this is the gradient, basically the gradient. And now the first variable is maximal torus valued. So you can, in this way, this X box belongs to the rearrangeable maximal torus of UN, kind of Cartan subalgebra. So the derivative of the first variable is actually is what I call B and 0 valued. So it is just basically the derivative of the first variable is just the real diagonal matrix valued. And with this notation, I can calculate the formula for the reduced first and second Poisson bracket. And both of them contain the dynamical R matrix and relatively simple formulas. So this is one result. And I don't explain the proof of this. I wrote the proof of those formulas here. But the basic point is that since a function on the gauge size, an invariant function on the gauge size determines the original invariant function. So also the derivative of this capital F can be expressed into the derivative of the restricted function. And this is how you do it. But this is technical point. Is it is only for people especially interested. So we have found the reduced Poisson bracket. And now what about the reduced dynamics generated by those Hamiltonians, which are the trace of powers of our Hermitian matrix? So originally we have these Bi-Hamiltonian vector with Vk on our phase space. And they give rise, they reduce, they project to vector fields on this gauge slice, because they come from invariant Hamiltonians. And I denote by Wk the reduced Hamiltonian vector field. And this is the formula. I mean, you have to give the derivative of Q and L, and the derivative of Q is also denoted by dot. It is given by this, and the derivative of L contains the R matrix. And so in a way, this is the reduced by Hamiltonian hierarchy. These equations. Well, because the functions on the gauge size are invariant, for example, by conjugation by maximal torus. So this vector field, this W is actually not determined. You can add anything which is residual infinitesimal gauge transformation. Anything which is generated by the algebra of the maximal torus of UN. Okay, so we obtain this kind of reduced Bi-Hamiltonian hierarchy. Now the nice thing is that it is this kind of Lux equation in dynamic array. But of course, this is only so more interesting if we can find some physical interpretation for this system. And now this comes next. How this is related to? I have two interpretations which are related to changes of variables. So the first interpretation, remember that this G slice S is this manifold. An element QL, Q is diagonal unitary and L is just arbitrary Hermitian matrix. So an arbitrary Hermitian matrix L, you can uniquely represent in this way. So this P is the diagonal part of L, and phi is an arbitrary off-diagonal anti-Hermitian matrix. And this will be an arbitrary Hermitian matrix in this way. So this contains the diagonal part, and this encodes the off-diagonal. And so let's use as our variable instead of capital Q and L, let's use the P which is here and the phi which is here. And basically this capital Q, maybe you write it in exponential manner. And then in terms of these new variables, first of all, the most important Hamiltonian, as always, the trace of the square of the Lux matrix. This will be the spin-Sutherland Hamiltonian, which I mentioned at the beginning. And also the Poisson bracket takes a nice form. The Q and P are really, this means that the Q and P are canonical conjugate pairs, Darboux variables. And the phi variables kind of, I call it collective spin variable. It decouples from the Q and P. That is, there's no cross term in the Poisson between phi and the Q and P. And this Poisson structure, this Poisson depends on phi. You can recognize that this is just the reduction of the dual space of the Lie algebra of UN by the maximal torus at zero value of the moment. So there is residual torus symmetry here, and this corresponds to kind of auxiliary Hamiltonian reduction. So the first Poisson structure, and in terms of by parameterizing the variables in this manner, and then the first Poisson structure takes a nice form, and this kind of main Hamiltonian takes also some nice form. So this is, of course, this is well known, this derivation of the spin-Sutherland model. And now there is also another interpretation which may be more interesting, and this has to do with the second Poisson structure. And I call the interpretation of the spin-Ruijsen-Schneider model. This is not the spin-Ruijsen-Schneider model which was studied, for example, by Kitchener and Zablud. It is a different model. To mention for those who may know about that. So we restrict to the part of the phase space when the Hermitian matrix is positive definite Hermitian matrix. So positive definite Hermitian is exponential of some Hermitian. And this is an open submanifold. Okay. And a positive definite Hermitian matrix can be parameterized like that. This B, I don't know, upper triangular. This means an upper triangular matrix is once along the diagonal. And P was the P is real diagonal matrix. So you write a pretty definite matrix, PB dagger as people say, sort of upper Borel matrix and adjoint of Borel matrix. And it can be written like that. So this will be the new. At first you introduce the new P and this B upper triangular, and then so this is a new variable, and then there's another step. Introduce new variable lambda, which is this group complete. And one can show that these are invertible, these are diffeomorph, these are invertible changes of variables. So instead of the original QL, now we use the variable the Q, P, and lambda. And lambda is again upper triangular matrix, complex upper triangular matrix with ones along the diagonal. And in terms of these variables, the second Poisson bracket takes this. Now, the second one takes this form. This Q and P form now canonical pairs, and this lambda part, you can recognize it as coming from some Poisson Lie group theoretic interpretation. So in the linear case, we had the reduction of the dual space of the U and E algebra. Now we have the reduction of the dual Poisson of U. Pn, which is upper triangular matrices with positive diagonal. This is a Poisson Lie group, and you can reduce by the maximum tools of UN at some trivial value of the moment map, and then it gives you this Poisson structure. So the second Poisson structure is some kind of Poisson Lie analog of the first one. Okay, and if you take the simplest Hamiltonian from the point of view second Poisson structure, trace of this Lux matrix, and I can also write this totally explicitly, but it has this kind of structure, this exponential of P and some sort of potential depending on Q and the spin, so-called spin variable. is left multiplication and right multiplication for the group variable. And of course, since I used right trivialization, right multiplication, so the action of the first copy, it is like that. So un times un like that. And now to parameterize the quotient space, you can use the, maybe in linear algebra it is called singular value decomposition. You write or KAK decomposition in Lie theory. That you write this GLNC matrices as unitary, positive, diagonal, and unitary. And you can write every element like that. There is some ambiguity by action of the maximal torus of un, and also by you can fix the y. There's also, so you can order these eigenvalues, okay. And so every invariant function sort of there is a natural kind of gauge size here that you have un times un. You can remove this un factors from the group value variable, and so the gauge size here will be this positive real matrix, diagonal matrix, and arbitrary GLNC matrix, and we again restrict ourselves to dense open submanifold when these singular values are not equal. And then again, invariant functions on the regular part will be torus invariant functions in this case, right? Because the torus still like, because it goes through this exponential field, and it will act on L. And again, you can compute formula of the reduced Poisson structure for functions on this gauge size, which are invariant on the torus section. And then I only so there's a complicated formula which are computed, and you can and then you take the first Poisson matrix. You can parameterize. Let's use a certain parameterization which leads to a physical interpretation of the model. Namely, this L is supposed to be an arbitrary GLNC matrix, n-by-n complex matrix. So it has some Hermitian and anti-Hermitian part. So P is the diagonal part of the Hermitian part. The psi left is the anti-Hermitian part, and the off-diagonal part of the off-diagonal part of the Hermitian part is coming from this side right. So these are two the psi left and psi right are anti-Hermitian matrices, diagonal part, off-diagonal part. And it turns out that they are coupled by this fact that their diagonal parts are opposite of each other. And in terms of these variables, the Poisson bracket again takes a nice form, the Q and P form Darboux pair, and you can recognize that the psi left and psi right, they correspond to, you have the un plus u, I mean the dual space of un plus un, and you reduce by the diagonal action of the maximal torus, the zero value of the moment. The moment is just you put to zero the sum of the diagonal part of the first copy and second copy, and this corresponds precisely to this constraint. Okay, and as I mentioned, this model was studied also by other colleagues, but without the Bi-Hamiltonian structure. And finally, if I think I still have a few minutes, yes. So I have another application is still the main idea. So you see, I'm always working with GL, GLNR, GLNC, UN, and this is so because I have this, the first perspective, the leader of the second one, and it's always along a vector field in which shift by the unit matrix are involved. So somehow what I'm saying that this seems to work for this GLN type groups and not more generally. Okay, so the final application is I want to put into this setting some non-compatible Poisson structures on the GLNR, the associative algebra actually. Also, Lie algebra is an associative algebra, and namely, let's consider this Lie algebra. Let's consider decomposition into sum of two subalgebras. So A is just orthogonal subalgebra, skew symmetric matrices, and B is upper triangular subalgebra, or kind of Borel subalgebra. And let's consider the difference of two projections. This is well known to be solution of classical modified Young-Best equation. It's not anti-symmetric. It's anti-symmetric part. It can be decomposed into anti-symmetric and symmetric part with respect to the trace bilinear form. And the anti-symmetric part is this Drinfeld or Drinfeld-Jimbo army on the real Lie algebra. Now it is well known for a long time from the work of these people that that there are two Poisson brackets on the GLNR Lie algebra constructed out of this army. And this first so-called first Poisson bracket is just the linear R matrix bracket, which is well known in the integrable system theory. The linear R matrix bracket is here. But there is also this quadratic bracket in which the symmetric part of the R matrix appears. And these two brackets are compatible. And also these trace functions, they satisfy this Bi-Hamiltonian relation. And these are the flows which they generate on GLNR Lie algebra. So what I'm saying that this also has, this also has an interpretation in Hamilton induction. But before saying that, let me mention that it is another well-known fact that so we have this compatible Poisson structure GLNR algebra, GLNR associative algebra. Now it is a fact that the symmetric matrices form a Poisson subspace with respect to both of these Poisson structures. And also the tri-diagonal symmetric matrix form a Poisson subspace, Poisson submanifold with respect to both brackets. And this gives the open Toda lattice and the so-called full symmetric Toda lattice. Okay. And it's also known that how the linear bracket comes from Hamilton induction. This is known from old works of Riemann, Semyonovsky, and Shansky. So the new thing which I'm showing in the last page of my talk is how the quadratic bracket arises from group theoretical method. Now you take the cotangent bundle of GLNR group, trivialize its usual manner, and we have the same formula. We have two compatible Poisson structures written in the same way. I did not write it, but the same in terms of the Drinfeld-Jimbo R matrix. It is the same as I had in the GLNC regarding the real. Just the pairing is the trace. In that case, it was the real part of the trace. So there are two compatible Poisson structures here, and then simply both of those Poisson structures have the proper one of them was just the canonical, but the other is quadratic Poisson structure. And both of these have the property that now I take this. Now I'm going to do Poisson reduction by another group which I call S. So the other group is just what appeared in the splitting into the classical R matrix. So A is the orthogonal group and B is Borel subgroup. So it is just upper triangular matrices with positive diagonal ends. Real matrices now. So the functions which are, and this is well known to be symmetric group relevant for getting Toda and goldfish model, which you heard last week. So we can so it turns out that both of these Poisson structures have the property that the invariant function close with respect to the natural action of this group, and the orthogonal group acts by right multiplication, and this Borel group. Sorry, the Borel. In that case, the nilpotent group was used. Sorry, I was not precise here. So we act by the symmetric group in this way. So left multiplication by the orthogonal and right multiplication by the Borel group, and trivialize the cotangent bundle. So this is the orthogonal. And then simply because we have the QU factorization or Gram-Schmidt procedure or Iwasawa decompose, we can write any GLNR matrix as a Borel times orthogonal. So this means that in this case we have the natural, we can really construct the quotient spaces really as a manifold, because simply the group element by these transformations, the group element G can be transformed to unit matrix by orthogonal and Borel multiplication from left and right. So every every invariant function, capital F and two invariant functions, capital F and capital H on the original phase space give rise to unique functions on the GLNR associative algebra, little f and little h. And then we just compute the original Poisson bracket in terms of these representatives of the invariant functions. And then they give those two Poisson brackets which I started with. So it is some kind of explanation of this quadratic Poisson structure in terms of Hamiltonian reduction theory. So, and I wrote some little paper with the students. And finally, so I'm at the end of my talk. So just to summarize, so first we observed that these four cotangent bundles carry natural Bi-Hamiltonian structures. And then we have shown that if we take Poisson reduction of these structures, then we obtain these reductions, these Poisson reductions were studied previously for the first bracket. But now if we do it for the Bi-Hamiltonian structure, then we obtain Bi-Hamiltonian structures for the corresponding reduced systems. And some of them are well-known classical integrable systems. So we obtain Bi-Hamiltonian structures for spin Sutherland models and these two spin variables, or for symmetric Toda lattice, we cover known Bi-Hamiltonian structures. Okay, I did not touch on this talk in the subject of degenerate integrability or superintegrability, but actually all these systems, all the reduced systems are also superintegrable. Actually, they are superintegrable with respect to both Poisson structures, as far as at least on the reduced Poisson manifold. And as usual, you can have various results, but they usually lead to more questions like it would be interesting to extend this construction to analytic spin Sutherland models, for which I don't know Bi-Hamiltonian structure, or actually sort of my main question in this subject for me for several years is that how to obtain the hyperbolic Lewis-Schneider model by Hamiltonian reduction. This is one of the real, I mentioned in the second slide, this repulsive many particle model which has to do with sine or solitons. And for that model, in my understanding, no Hamiltonian reduction treatment is known. This is still an open question. But I don't know what to start, what to reduce. So if anybody has some idea on that, I would appreciate. And I finished my talk. I just mentioned that actually I put detailed derivation of various things. If somebody is interested, he can have a look, and I'm also quite happy to communicate about it. Thank you very, very much.
Okay, thank you for the talk. Questions?
So please.
Hello. Did you study system dual to these two spins Sutherland model? PQ dual.
So I don't understand the question.
Did you study model PQ dual to the two
Oh, I
spin?
see. Sorry. No, I did not study. But I think yes. No, I did not do that. But I think it's a good question, and it's possible to do. I understand.
Okay. And second question: do you have any idea? Can you quantize your two spin system?
Quantize. Well, certainly for this, let's put it this way: that for the spin Sutherland model, original model, quantization by quantum Hamiltonian reduction works. And that I also, so it's not well known, but in particular I also considered it. So with respect to the first Poisson structure, certainly quantum Hamiltonian reduction should be possible to apply. Keep some spherical functions with respect to UN times UN group in some representations. But it's always it is also a natural question to ask how you quantize the other Poisson structure. That I don't want. Actually, the other Poisson structure has to do with Poisson Lie group. So maybe that's also possible. So the more involved quantum Hamiltonian treatment in the sort of quantum group theories should be possible, but I haven't done it.
More questions? Okay, if no, thank you for your talk again.